Okay, we are discussing about model seeking algorithm, and in this model seeking algorithm what happens, we have seen that we need one model as input and one CTL formula as another input, and our model seeking algorithm will look into the states where this particular formula is true. Okay, now today we are going to see this particular model seeking algorithm with some other constraint which is known as your fairness constraint. Why we have to look into the fairness constraint, why it is required? For that we will just see our general model seeking algorithm with an example. We will try to devise an example, we will go through the example, and later on I will say why these fairness issues are coming into picture and how it is going to help us during model checking. Okay. Now, just first we are going to look at design issues, that was an example, design a controller for a microwave oven. All of you know that microwave oven is used for cooking food. So, it is automatic. So, we should have a controller to control the operation of this particular microwave oven. Now, when we are going to design a controller, initially we are going to look for an abstract model of that particular controller, and depending on that particular abstract model we will design it. Later on we can refine it and we will go for more details. Okay. Now, when you look into it, then what is the requirement for this particular controller? We know that there is a door for your microwave oven. We can either open the door to put food item inside the oven, and we can close the door. That means we need some mechanism, and generally it is a sensor which will sense the signals and say that either door is open or door is closed. Later on, after putting the food items and after closing the door, we can start the oven. When we start the oven, then what will happen? The heating coil will heat it up and eventually the food will be cooked. So, by looking into all those issues, we can come up with a very simplified model initially, simplified abstraction, and we will find that some of the things or some of the signals required to model this particular controller. So, those signals are basically we are abstracting out, and we are saying that first one is start. It is going to say that the oven has been started. Now, it is going for cooking our food item. Close basically indicate that whether door is closed or door is open. When we start, that heating coil will be heated up and food will be cooked. So, we can say that another important issues that we need is heat, and sometimes the oven may go into the error situation. So, you can take another signals called errors. So, with the help of these 4 signals, we are trying to or will design our controller. So, this is some sort of abstraction. Later on we may have to refine it and we can go for the complete design, but first we will see this particular abstract model and we will see how we are going to look for the property that has to be satisfied this particular model. Now, with these particular things, now what you see that now we have to look for the states. So, basically we can see the operation of our microwave oven. Just see that first we are saying that this is a state, I can mark this as a S1. I am saying that not of start, not of close, not of heat, not of error. That means the microwave oven is in ideal situation. It has not started, door is not closed, means door is open. You can say it is not heated up and there is no error condition. Now, these are the action that I can say that I can close the door, then it is coming to this particular state whether not start, close, heat and error, because it was door was open, now door is closed. Now, when you close the door, the user may again open it, because he may have to put some more items. So, he can be in this particular loop. He can close the door, he can open the door. But sometimes it may happen that we are in the ideal situation, ideal condition. Now, somebody has started the oven. Now, it is not closed, that means door is open. So, in this particular case he has started the oven, then now what will happen? This is start becoming true and it has gone to the error condition. Now, when it has gone to the error condition, now user might have realized and he is going to close the door, but again it is still in the error condition, he will open the door. So, he may be in this particular loop trying to open it. So, we have given an option reset button. Through reset he can come down to this particular things. Now, say my door is closed, it is not in error condition. Once we are coming to this thing, then we can start the open. So, start is true, close and not it, not it. Then we can go for a warm up, that means we are starting the heat. So, heating coil is heating up, then we can start cooking. So, it will remain over here and it will when it's complete, then coming to this particular thing, that door is closed, then you can open the door, or straight away you can open the door and come to this particular. So, this is the simplified operation of a micro oven. So, now in this particular case, now you see that when we go for model seeking, we need a Kripke structure. What is a Kripke structure? It is having set of states, we are having transition, and we are having labeling function. So, these particular events are not required for our model seeking, that start open, close door, open door, reset, warm up, all those things are not required, but we need the other information, that those states, this labeling function and this transition. So, basically what happens, you can say that eventually we have come up with this particular model, and this is a simplified model, and within this particular model or in this Kripke structure, we are going to check some of our properties. Okay. Now, what are the properties that it should satisfy? So, I am just coming up with two examples. First one, I am saying that microwave oven should not heat up with its door open. So, when is door open, so coil should not get heated up, because still we are going to put some more water. Second property, we are saying that once you start the oven, eventually it must turn on the heating coil. So, once you start the oven, it should go for the cooking mode. So, heating coil must be heated up. So, these are the two properties. Now, how we are going to check these things? So, we know that we are looking for CTL model seeking. So, somehow we have to represent these two properties in CTL formulas. So, the first one is very simple. So, basically not of close and not of heat should not be true together. So, that is why we are saying that not of close and heat. So, these two combinations, not of close, that means door open and heat, it should not be true together. So, negation in front of that, we are putting that negation, and it should hold globally. So, in all part globally, this property must hold. Second one, I am saying that once we start the oven, eventually it must turn on the heating coil. That means, when we are turning on the heating coil, that means oven will go into the heating condition. So, I am saying that in all part globally, start implies AF in all part in future heat is true. So, I am capturing this particular property with the help of this particular CTL property. Now, I have these two CTL property according to my requirements, and we are going to check whether these two properties are true or not. If you look into the first property, it is simply based on the atomic proposition. I am having one atomic proposition closed and one atomic proposition heat. So, we have to check whether in which situation, in which state they are true or they are false, and depending on that I can look for the AG. And second one, I am having one start and heat, again AF and AG. AG is involved in bouldering. So, I am going to check the property for a second. First one will be simpler one, and you can check it yourself. We will see how I am going to check this particular second property. Okay, now, we are having this particular Kripke structure or model of our system microwave controller, and I told you that we are going to check for the correctness of this formula. In all part globally, start implies AF heat. So, first we are going to see that we have to look for each and every sub formula. First we are going to look for this particular sub formula heat. Now, by looking into this Kripke structure, you will find that heat is true in state S4 and S7. So, this is S4 and this is S7, this is heat is true in this two scenario. Now, by looking into this thing, since it is true, now we have to go for, we know which are the states where heat is true. So, we are getting S4 and S7. Then we will go for the next sub formula AF heat. So, AF heat. Now, we have to see how we are going to look for the correctness of this particular AF heat. So, how we are going to do? We know this temporal operator AFC1. Now, what will happen if any state that is S is labeled with C1, label it with AFC1. This is the first steps. Then we are going to repeat this procedure. Label any state with AFC1 if all successor states are labeled with AFC1 until there is no sense. So, we know this particular step. Now, we are going to apply this algorithm to look for the states where AF heat is true. So, now in this particular case, so we know that AF heat is true in S4 and S7 because heat is true in these two states. So, this is our first step. Now, after that we will go into that particular repeat step. Now, what will happen next? We are going to see where it will be true. So, S4 and S7 we are getting it. Now, we are going to see what are the predecessor state of this particular two states. So, S4 it is having its own predecessor and S7 is having S6 as a predecessor. Now, only predecessor. Now, what will happen? We are going to label a state if all of its successor are labeled with AF heat, since it is having one successor and it is labeled with your AF heat. So, S6 will also be labeled with AF heat. So, in AF heat will be true now S4, S7 and S6. Now, since there is a change of the state, so we are going to repeat this particular process. Now, if you look into it, then S6 we are going to get this S3 as a predecessors, and in this particular case it is having this S3 is having this particular successor, and this is the scenario that we are having. Now, what will happen? It is having this particular predecessor S3. Now, we are going to see all of its successor. Now, what are its successor? One is your S6, okay, and second one is your S1. So, in case of S3, you will find that it is having this particular successor. So, S3 will be labeled with your this particular AF heat. Next, we will go and we will find that it will remain is your AF3, because when I am coming to this particular S3, so it is having this predecessor your S1 and it is having this predecessor your S5, but they are not labeled with your AF heat. So, we cannot include S1 and S3, S5. So, our state remains same S4, S7, S6 and S3. So, these are the states where AF heat is true. Now, once we know the states where AF heat is true, now we can go for this particular sub formula. Start implies AF heat. That means, if start is true, then AF heat must be true. So, in this particular case, how I am going to say that? These are the states S4, S7, S6, S2 and S5. These are the states I am getting, because it is not of start or AF heat. So, we know that AF heat is true for S4, S7, S6, S3. So, these are the states, and along with that not of start is true over here. So, not of start, because we know that P implies Q is your not of P or Q. So, in this particular 4 states your AF heat is true and not of start is true in S1. So, S5 will also come into your this particular scenario. So, ultimately we are going to get these are the states where start is true, and eventually we are going to get AF start implies AF will be true in your S4, S7, S6, S3 and S1. So, I am going to get these particular states. Now, after that, once we know the labeling of this particular sub formula, then we can go for main sub formula. So, in this particular main sub formula, what will happen? Now, we are having this particular AG start implies AF heat. We know the procedure. Now, what is the procedure for AG? So, how we are going to get? So, in step 1, label all the states with AFP. Then, if any state as is not labeled with P, delete the label AGP. Okay. So, basically initially we are going to check where AGP is true, then we will repeat this particular steps. Delete the label AGP from any state if all of its successors are not labeled with AGP until there is no sense. So, we are going to repeat this step 3. So, if you look into this procedure, then what will happen for AF start? Initially, we are going to label the all state, then we will remove where it is not labeled with your start implies AF heat. So, these are the states where start implies AF heat is true. So, AG start AF heat will be true in your S4, S7, S6, S3 and S1. In this particular 5 state, it will be true, these 2 states will not come. Now, we are going to repeat this particular step 3. Delete the label AGP from any state if all of its successors are not labeled with AGP until there is no sense. So, we are starting with this particular state S4, S7, S6, S3 and S1. Now, we are going to repeat this step and see what are the states will eventually remain over there. Now, in this particular case, you just see that S1, it is having successor S3 and it is having successor S2. Since all the successors are not labeled with start implies AF heat, so we have to remove S1 from this set. So, eventually I am getting this set as S4, S7, S6, S3. So, I am going in once inside the loop. Now, we will see again, since there is a sense, we have to go again inside this particular loop and we will find that now when I am coming to this particular state S3, now how many successor it has? It is having successor as S1 and it is having successor in S6. Now, S1 is not labeled with AG start implies AF heat. So, we are going to remove S3 even. So, we are going to get S4, S7, S6 as the remaining set. Now, from these particular things, now we will look again this particular condition, and what will happen in S4. Now, you just see that it is having S4 as its one successor, it is having one successor in S3 and another successor is S1, but this AG start implies AF it is not true in S3 and S1. So, we are going to remove S4 also. So, ultimately we are remaining with S7 and S6. Now, when we come to this particular state, now when we come to S7, it is having one successor S6 and it is not labeled with this particular formula. So, we will remain S7 from here. Now, when I am coming to S6, then you will find that it is having one successor S7, it is not labeled with AG star, it implies AF it. So, we remove that one also and eventually we are getting an empty set. That means, in none of the state this particular formula is true. So, that means, AG start implies AF it is not true in this particular model. So, now what we are going to do? Now, we say that we have come up with a model and we are looking to check for a particular formula, and eventually we will find that after going through our model checking algorithm, we found that this particular formula is not true. Now, in this scenario, what we have to do? We have to revisit our design and try to modify the design in such a way that the given formula or given property will be true in our model. But if you look into this particular model, up to some extent we will find that this model or this design is somewhat correct, because the designer will convince it, but my model checking algorithm is saying that it is not correct. Now, either I have to revisit it or whether can I do with something else. Now, we are going to look into that particular issue. Okay. Now, either we can revisit our design or we can look for a correct sequence of our operation. It may happen that when we are going to look these things, that when we are going to look for verification of properties in our model, it may happen that we are having some unrealistic behaviors. Due to that unrealistic behavior, it may happen that the given property is not true in our model. So, somehow what we are going to do, we are going to filter out this particular unrealistic behavior. Okay. Now, just see this particular example. If you come up with this particular model, now if you find that if you look for these things, we are saying that start implies AF heat. Okay. If we have started a heater, then eventually on part, in all part in future it should be heated up. Now, we have seen that this particular formula is true in this particular 5 state. Okay. So, this is true in this particular, and when, but it is not true in these 2 states. So, that is why when I am going to look for AG of these particular things, due to these particular states, it is not true in our model. But what is happening over here? You just see that, you know that this is we are starting it, then we are closing the door, since it is not going to heat it up, again we are opening the door. So, closing and opening we are doing over here and we will be repeating over here. So, this is some sort of a unrealistic behavior. We know that eventually user will realize his mistake and he will reset his button, and eventually it will come to this particular state. When it is coming to this particular state, you see that eventually it will go to heat up the coil. So, this is I am talking about that it may have some contains unrealistic behavior. Okay. So, this is unrealistic behavior, but we cannot avoid it while modeling our system. So, now what we will see that whether can you go with this particular unrealistic behavior or not. So, that is why we are going to say that we will put some constraint while doing the model checking, so that it is going to remove those particular unrealistic behavior. So, the constraint that we are going to put is basically known as our fairness constraints. That means, we are going to look for a fair system. We are going to put some fairness constraint in this particular, with the help of this fairness constraint. What we are going to do? We are going to eliminate such type of behavior. That means, we are going to look the model only in the fair part. So, because eventually we know that user will realize the mistake and it will press the reset button and it will come to this particular state. Once it is coming to this particular state, eventually coil will be heated up. So, this is the notion that we are talking about, the fairness constraint. So, we will put some constraint which will filter out the unrealistic behavior of the system, and it is going to do the model checking on the fair parts only. That is why we are saying it is a model checking with fairness constraint. Okay, now how we are going to do this thing? So, we are going to filter out those particular unrealistic behavior. So, in this particular case, how to filter out this particular unrealistic behavior? We are going to again do it with the help of our CTL formula only. Now, what will happen when I am going to model check a particular formula in a particular state as M as model psi. In this particular case, instead of modeling M as model psi, we will try to verify M as model psi implies phi. So, what we are going to do? We are going to model check M as model psi implies phi. What does it mean? Where psi encodes the refinement of our model expressed as a specification. So, what is this particular psi? It is nothing but a refinement of our model, and we are expressing this particular refinement with the help of another specification. So, which is another CTL formula. So, we are trying to capture these things, that refinement of our model with the help of a CTL formula. Now, we will see how we are going to do it. So, in this particular case, what will happen? Somehow we have to put some constraints, so that it is going to eliminate this particular unrealistic behavior. So, we are trying to capture this particular unrealistic behavior with another CTL formula psi. That means, we will say that when psi is true, then phi is true. So, that means, psi implies phi. We are going to check for the correctness of psi implies phi. That means, whenever psi is true, then look for the correctness of phi. So, in this particular case, what we can say that if psi is true infinitely often, then phi is also true infinitely often. So, that means, if psi is true infinitely often, if it is infinitely often false, then phi cannot be true. But if psi is true infinitely often, then we are going to say that phi is also true infinitely often. So, we are capturing this behavior with the help of this particular formula. Model M in status psi implies phi, where psi is the refinement of our model expressing as a CTL formula, and phi is the formula or the property that we are going to check in our model. So, we are saying this is the model checking with fairness, and this psi is going to basically give us the fairness constraint, and if psi is true infinitely often, we will say that phi is also true infinitely often. If psi is not infinitely often true, that means, it is just going through some unrealistic behavior. It will be in some loops where this particular psi is not true, but we know that in the system eventually it is going to come out from this particular loop. So, that is why we are trying to filter out those particular part, and we are going to filter out with the help of this particular constant psi. Now, in general, now what we are going to say that instead of one particular fairness constant, we may have several fairness constants. So, we are going to say that let C is equal to psi 1, psi 2, psi n be a set of n fairness constants. So, we may have several fairness constants, and we say that C is a set of our fairness constants. So, we will say that a computation path S 0, S 1, S 2 like that is a fair with respect to this fairness constant if for each I there are infinitely many j such that psi j model psi I. So, that means, we are going to look for a path. In that particular path, those particular psi i's will be true infinitely often. So, in general situation, what will happen? We can say that, and we write these things as A C and E C for the path quantifier A and E restricted to fair path. So, A C basically says that this is all path through this particular fairness constraint, that means, all fair paths. E C, there exists a path with respect to given fairness constraint C. That means, we are looking for a particular fair path. So, we are having a set of fairness constraints. Now, we are going to have the path quantifier A C and E C instead of general A and E. Okay, now, we write A C and E C for that path quantifier A and E restricted to the fair paths. Now, in this particular case, now what will happen? We can say that we are having the formula A G phi. So, that means, whether in all paths globally phi holds or not. So, this particular formula, if we write A C G phi, what does it means? Whether this phi holds globally in all fair paths. That means, in all paths where this particular fairness constants are satisfied. Okay. So, that means we are going to look for all fair paths. That means, with fairness constraint we may have such type of scenario M S0 model AC G phi if phi is true in every state along all fair paths. So, similarly, we can define for ACF, ECU, etc. That means, AGP is all path globally phi holds without any fairness constraint, but ACGP says that phi holds globally in all fair paths. That means, in all the paths where the fairness constraints to C is true. Okay. So, this is the way that we are going to look into it. Now, we can say that a computation path is fair if any suffix of it is fair. So, we can say that now you say what happens if I am going to say that this is a path, say I am coming from S1, S2, S3, S4, S5 something like. I can say that this path is fair enough if any one of its suffix is fair. That means, if I can establish that this is the suffix of the given path, say this is your path pi, then pi 3 is the suffix of this particular path starting at this particular state S3. Now, if pi 3 is fair, then we can say that pi 2 will also be fair, because since its suffix is fair. So, we are going to say that a computation path is fair if any suffix of it is fair. So, if we can establish that any suffix is fair, then we can look into that the particular path will also fair, because ultimately eventually it will go to that particular suffix. So, in this particular case, now what we can say that we can look for your model checking formulas similar to something like that. So, if I am going to say that any suffix of a path, if it is your fair suffix, that means we can say that what I can say in this particular case. So, what we are saying that a computation path is fair if any suffix of it is fair. So, basically if you consider any path something like that S0, S1, S2, S3, S4 like that. So, if this is path pi and if you consider any of its suffix, say this is your pi 2. If we say that pi 2 is fair, then we can eventually say that pi 1 will be fair and we can say that pi 0 or pi will be fair, because eventually it is going through this particular fair path. So, that is why you can say that if in our formula what we are looking into it AC G phi. Okay. So, we are saying that AC G phi. Now, if I say that AC GT. So, what does this means? That means in all state, we know that in all state it is labeled with your truth value true. So, that means if we say that GT basically talk about a path where true is always true, but along with that instead of A we are saying that AC, that means it is the path where this particular fairness constraint is true. That means eventually we can write that AC GT. So, this is basically talk about this particular suffix where this suffix everywhere true is true, but it is your AC means that means the fairness constraint C is also true over here. That means, for these things we can say that if a suffix is fair, then this part will also be fair. So, in that particular case what we can say now, say we are going to look for say EC phi until psi. So, this is basically there exists a path where this particular fairness constraint is true phi until psi. That means, we are going to look for this phi until psi in fair path. So, we can say that this is equivalent to there exists a path phi until psi and ECGT. So, this is your fair path where true is always true. That means, we can say that eventually when I am talking about that EC, that means there exists a path with fairness constraint phi until psi. We are talking using the general E, that general E until operator without any constraints. So, we are going to look for phi until psi, but along with this particular pair part E c g t. So, similarly, for E c x phi, what you can write that E x phi and E c g t. That means, we are going to look for the next state where it is a fair enough. So, E c g t basically talk about the fair part, that means the part where this particular fairness constraints C are true. So, you just see that if it is your E c until operator and E c x, that means until there exists a part with fairness constraint until and there exists a part with fairness constraint next step. These two are can be represented with the help of E c g t. That means, eventually we will find that we need a procedure for either E g t, E c g t or A c g t. These are very similar. So, basically what happens? We need the procedure for either E c g phi or A c g phi. That means, once we have a procedure for E c g phi, then we can talk about E c g t, or A c g phi we can talk about A c g t. So, we need procedure for this one, then even after that what will happen? E until and E x can be expressed with the help of E c t g t. So, basically we need procedure for either A c g phi or E c g phi. If we have the procedure, then we can have the model checking procedure for with fairness constraint. Okay, now, just see what is the procedure for E g phi. Already we have checked it. We have another procedure. We are saying that restrict the graph to start to state satisfying phi. So, first step is we are restricting the graph to a state where it satisfies phi. Then find the strongly connected components SCC of the restricted graph. And as a third step, we are saying that use backward breadth first searching to find the states on the restricted graph that can reach an SCC. So, with the help of this procedure, we can talk about E g phi. Okay. So, basically what happens? You can say that if I am having some state so, we can say that this is your SCC, because all state can be reached from any other state. Now, from this particular state what will happen? We will follow the backward sorry, my arrow will be in this direction, backward breadth first search, and if I get any state, then we can say that this is basically we can reach over here, because if we are looking for P, if P is 2 over here, because it will be P is 2 will also be over here. So, in this particular way we are going to collect all the states. Now, in third what will happen? Now, we are going to look for E c g phi. Here exists a part with fairness constraint g phi is true. Now, this is also similar to that procedure, only what we are going to say that first step restrict the graph to state satisfying phi, find the strongly connected component SCCs of the restricted graph, already we have discussed. Now, we are having one particular condition over here, remove an SCC if for some psi I it does not contain a state satisfying psi I. The resulting SCCs are fair SCCs. Now, we will just give an example. So, we are saying that infinitely often all psi i's must be true. So, if it is not true, then we are going to remove those particular SCCs. Again, the fourth step is similar, use backward breadth first searching to find the states on the restricted graph that can reach a fair SCC. Okay. Now, you just see that. Now, I am giving an example, say so, I know that these are the state S0, S1 and S2. So, this is an SCC, we do not have any problem. Now, you just said that I am having a fairness constraint C is equal to say psi 1 and psi 2. Okay. Now, what will happen, say in this particular state S1 says psi 1 is true and in this particular state says psi 2 is true. Now, in this particular case, whenever I am coming to say from some other state, if I am coming to this particular state, then what will happen? You just see that it will be in this particular loop, it can go over. So, infinitely it can go over here, but wherever it go at some point of time psi 1 will be true or psi 2 will be true. Okay. So, I can say that this is an fair SCC. Okay. But if I talk about a fairness constraint, say this is C 1 and C 2, and I am talking say that psi 1, psi 2 and psi 3 are fairness constraint. Now, when I come to this particular SCC, okay, in this SCC wherever I go I will find that psi 1 will be true, wherever I go I will find that psi 2 will be true. So, in none of the states in this particular SCC strongly connected component psi 3 is true. So, that means, if I remain in this particular loop then psi 3 is not going to be true. So, that means, this fairness constraint psi 3 is not satisfied over here. So, I am not going to say that this is a fair SCC. So, as per the third step of my algorithm, we are going to remove this particular SCC from our graph. So, this is the things that we are talking about, that remove an SCC if some psi I it does not contain a state satisfying psi I. The resulting SCCs are the fair SCCs. So, that means, we are just keeping only the fair SCCs. So, if it is fair SCCs, that means, whatever fairness constant we are giving those will be true over here. So, this is the model checking algorithm with fairness constraint. You just see that once we have this procedure A g or E g, then other operators can be defined with the help of that E g or E g. So, eventually we have seen that we have got a procedure for model checking with fairness, and we have discussed here with E c g phi. So, this is similar to your E g phi, except that we are having one particular step over here, where we are going to remove the unfair SCCs or we are going to keep the fair SCCs. Now, you just see that what are the procedure that we will be needing for your model checking algorithm with fairness. Say we need either one E until or E x or say A g or say A f. Now, we have seen that with only A c g or E c g, if we know the procedure for A c g and E c g, then we can look for the procedure for E 1 E x, because E c is again expressed with the help of the normal E operator, and E c x again expressed with the normal E x operator, but along with that we are having this particular fair suffix. So, E c g t and E c g t, that means, where the fairness constant applies. Basically, we are going to keep all the fair SCCs. So, this is the notion. So, we are having now we have seen the procedure for E c g, or similarly we can construct for A c g also. Now, after knowing this particular fairness concept, let us come back to our example that we are talking about, that microwave oven examples, and we have come up with this particular model which is having 7 states, and we tried to check for this particular formula A g start implies A f heat. Now, when we apply our normal model checking algorithm, what we found that these formulas is not satisfying this particular model. Now, one option is we should go for defining of this particular model, come up with an alternative solution, or secondly, we have seen that it can go away or remove or prevent those particular unrealistic behavior and try to check this particular formula in realistic behavior only. And for that we have to apply fairness constraint. Now, we have seen that this is some sort of unrealistic behavior, that closing and opening the door repeatedly after starting it. So, we are trying to remove this particular unrealistic behavior. So, how we are going to do this thing? That means, we are going to do it with the help of some fairness constraint. Now, what will be the fairness constraint over here? So, what is the fairness constraint that we are going to look for it? Start, close and not of error. That means, when it go to start and close situation, that it should not go into the error condition. So, not of error. So, this is basically that we are talking about the C is a set of fairness constraint, where I am having psi 1, psi 2, psi 3 as my fairness constraint. So, here the fairness constraint is start, close and not of error, and we are going to look for A g start implies A f hit. already we have seen the marking of start implies AF heat, and we know that these are the states where start implies AF heat is true, S4, S7, S6, S3 and S1. Now, along with that we are giving this particular fairness constant start, close and not of error. Now, we will see how that model checking with fairness constant will be used to check for this particular formula. Now, what will happen in this particular case? Now, as for our these things, we are going to restrict the graph with the states where this particular formula start implies AF heat is true. So, basically we will find that these are the states where this particular formula AF start implies AF heat is true, because in the other two state S2 and S5 this formula is not true. Now, after that what happens? We have to look for those particular fairness constant. Now, as for our example, now we will see that what are the SCCs over here. Once you will get the SCCs, then you will see whether in this particular SCC start, close and not of errors are true or not. You just see that wherever you go, you can look for this particular scenario. Say, I am having this is a loop. So, wherever you go, you can go to any other states. So, in this particular case, what will happen? You will find that either start is coming true, close is coming true, or not of error is coming true. So, infinitely often it is coming. Or on the other hand, if you can say that I can be in this particular loop. So, one of these particular fairness constants will be true. So, like that we can say that this is the remaining SCCs that we are going to have, and if you now apply this particular AG start AF heat, then you will find that in all those particular states this particular formula is true. That means, globally in all part globally start implies AF heat. That means, whenever you start the oven, eventually it will heat up the coil, because here what happens basically with the help of this fairness constant we are removing this particular unfair part. Okay. So, and we are going to check only on those particular fair parts. Now, you just see that with fairness constant eventually you say that okay, our model is going to work and it is going to satisfy this particular formula. But in some point of time, if user is going to be in this particular loop forever, then it is not, but we know that user will also use his own intelligence and eventually he will press his reset button and he will come to this particular point. So, this is some sort of a unrealistic behavior, and with constant fairness constants we are removing it and we are trying to check on property in the remaining graph. Okay. So, this is the way that we can check for our correctness. One is your refine your model, or secondly try to find out a constraint, fairness constraint, and model check on the fair parts only. Okay. So, this is basically we have discussed about the model checking algorithm. We need one model, we need the properties, those properties will be expressed in the CTL. So, these two will give as an input to the model checker, and it will model checker will give us the set of states where this particular formula is true. And sometimes what will happen, if we can identify that it is having some unrealistic behavior, but it is unavoidable, then we will try to identify some fairness constant and we are going to look for the correctness of the properties in fair parts only. Fair parts will be those parts where those particular fairness constants are true, and with this we can now proceed for a model checking, and we are going to check whether this property is true in this particular fair parts or not. Okay. So, this is in general, we can say that this is the things, or this is the concept about the model checking, and in any design we can apply this particular model checking algorithm before proceed further in our design cycle. Okay. So, what is this? Some come up with your design, express your properties in CTL and try to check those properties in those models with the help of model checking algorithm. But if the system is having some unrealistic behavior, then we try to filter out those particular unrealistic behavior with fairness constraint, and we will do the model checking on fair parts only. So, this is about the model checking approach for verification of our properties. Now, we are having now enough information about your model checking algorithm, and we know how to do it. Now, just look for some questions. Now, that one question that I am giving you now, design an elevator controller. I think in a multi-storied building all of you have used lift or elevator, and what you are having that you can press button to go to any floor, or it can give a request to the lift by pressing a button in this particular floor. So, for that we have to design this controller. So, we have to identify what are the things or what are the control signal required, and depending on that we are going to design a controller. Now, in this particular case, again as per our design principle, we are going to abstract out a model and we are going to identify the required control signal, and with the help of those control signal we are going to have a model. Once we have the model, then we are going to look for the properties that need to be satisfied by our controller, and we are going to check those particular properties. Now, in this particular case, I am coming up with a very simple solution, or I am just abstracting out the controller in such a way that we are having a very less number of control signals. So, this is the initial design. After that, we can go for refinement and put more and more information into our model. So, in this particular case, I am coming up with 4 signals. One, I am talking about MU, that means elevator is moving in the upward direction. MD, this is another event. I am going to say that elevator is moving in the downward direction. So, these are the signals indicating that either lift is moving upward or lift is moving downward. DO, basically door is open. Door can be either in 2 condition, it is open or closed. So, I can identify one signal as door open. LP, elevator is loaded with passengers, and ER, it has gone to some error condition, some error has occurred. So, we have identified this particular 5 control signals. So, these are the atomic proposition, either this will be true or false. Now, with the help of these things we can come up with a model. Okay. So, say this is a simplified model. I am saying that this is one particular state. What we are saying that this is not of LP, not of DO, not of MU, not of MD, and not of error. That means, it is in the ideal scenario. Now, depending on these things, when the moving upward or moving upward, then what will happen? Some of the signals will go as move upward will be true. This is your moving downward, and depending on these things, door open and door close, these are the events, and depending on that it is going into different scenarios and different states, and it is all the states are labeled with the control signal which are true over there. You can check it. Similarly, passenger in and passenger out, these are the events. Depending on that, it will go to some other state, and after that we can close the door. One close the door, then it will move upward or move downward, and without closing the door, if you again say trying to move out and move down, then it will go to the error scenario. So, these are the error scenario. By looking into the scenarios that and the event that is going to happen in while operating this particular lift or elevator, we can come up with this particular simplified design. Once we have this particular model, now we can look for the properties that need to be satisfied this particular model, and we can apply this particular model seeking algorithm to check for the correctness of our design. If the design is correct, then we can proceed further for fabrication and other things. If it is not correct, then what will happen? Our model seeker algorithm or model seeking algorithm will give a counter example, and it will say that if you follow a particular path or particular execution trace, the property is not true. And as a designer, what happens? We can revisit our design, or we can rectify those particular design error. Or on the other hand, if as a designer, if you convince that this particular behavior is an unrealistic one, then I try to identify some fairness constraint, and I will apply the model checking with those particular fairness constraint. So, this is the way that we are going to proceed. Now, once we have the model, then what we can say that what may be the specification on what are the properties. So, one simple property I am saying that the elevator will either move up or move down provided the door is closed. That means, the elevator should not have any movement if its door is open. So, these properties must be satisfied by our controller. So, another property I can say that an elevator traveling, say an upward traveling elevator at the second floor does not change its direction when it has passenger wishing to go to the 5th floor. So, this is basically the algorithm that you have incorporated in our lift controller, because we should have some protocol to give the service to the passengers. So, generally what happens, the simple procedure, a simple algorithm or simple notion, you can say that if lift is moving upwards, then what will happen? Generally it is going to service the request for all upward direction. Why? Because as a designer we know that if some lift is moving up and from some floor, if we are going to come down, then what will happen? There will be a change of direction in the motor. So, changing the direction of motor is going to consume power, energy. So, in a general notion, what happens? We are going to give the service to all upward direction first. If the lift is moving upward, then we change the direction, then lift is coming in the downward direction. So, that is why such type of properties we need to satisfy to check for the correctness of our protocols. But if you are implementing some other protocol, then this property may not be true. So, depending on the protocol that we have implemented or that we are using in our lift controller, we have to identify the properties and we need to check those particular properties. So, these are the specification. Now, what happens? You just see that we are having the model, we have come up with a model, we have those particular specification. Now, we have to represent this particular specification in your temporal logic formula. Now, you have having enough knowledge about your temporal logic, about CTL. Now, this is you take this as a task and try to write down the CTL formula for these two particular specification. Okay. Now, another question, you just see that what happens, already we have discussed about the mutual exclusion protocol. Okay. So, in this particular mutual exclusion protocol, we have come up with a model, and what we have seen that or what we have discussed that it is having two process P 1 and P 2. So, we are working with two process P 1 and P 2, and what are the states? We are saying that it may be in a non-critical region, it may be trying to enter into the critical region, or it may be in the critical region. So, we have modeled it and we have seen what are the properties it need to satisfy. Now, I am giving a question to you people. Now, you just check, design the mutual exclusion protocol for n processes. Now, we have discussed the mutual exclusion protocol for two processes. Now, I am saying that you extend this model for n processes. Okay. Now, what will happen? Now, we are having two processes P 1 and P 2, and we know the states, and eventually what we are doing? We say that come up with a combined model and do your job. Now, instead of two processes, now I am having n processes P 1, P 2, P 3 like that P n. Now, come up with a model and see how to model this one and how to model check those particular property. So, similarly, I can give you some more questions. You try to come up with a model and try to look for the specification or the properties that need to be satisfied. So, another simple question I can say that design a controller for traffic light. So, we are having a traffic light controller. Now, you should try to look or try to design this particular controller, so that we can control the traffic in a junction, and now try to come up with a specification of this particular traffic light controller and represent those particular specification in your CTL, and after that apply CTL model checking algorithm to check those particular property. Now, you just see that in just giving a simple hint. So, in a traffic light controller, then what will happen? Say, I am having a junction, road junction. So, it can say that it can go east to west direction or say north south direction. Now, what will happen? Here I can have three signals, red, orange and green. Okay. So, this is for east west direction, and similarly I can have red, orange, greens for your east west direction and say north south direction. Now, what will happen? Now, you say that what is the property? Is that both the red light should not glow simultaneously. Okay. On the other hand, I can say that both the green light should not glow simultaneously or at same time, because if you are glowing the green light together, then what will happen? Car will move from both the direction and there may be collision. So, what will happen? If our specification should be like that, both green light should not be glow simultaneously. Similarly, if one is red, if say north is or say north south direction is your red, then east west direction may go into green. Okay. So, these are the specification. Now, you have to identify those specification and try to write those particular specification in your CTL and design the controller, so that we can control the traffic correctly in this particular junction. Okay. Now, what we have seen that we have coming up with this model checking method, model checking algorithm. We are having properties we are having a model and we are going to apply model checking algorithm to check whether those properties are true in the model or not. Now, how I am going to get the model? We may have a problem, because you just see that if we are having n control signals, just say that if we are having n control signals, then what will happen? How many different combination we may have? We may have 2 to the power n different combination. That means, we may have 2 to the power n different possible state. All may not be reachable, because already we have seen our mutual exclusion protocol, where we are having 6 control signals. So, total state space is 2 to the power 6, but all may not be reachable, but we have to ready for the worst situation. So, if I am having one control signal and control signal, then we are going for 2 to the power n different state. Now, say in our design, if we have increased this particular control signal and control signal for n minus 1, say we need one more extra or additional control signal, then the number of state space will go to 2 to the power n plus 1. Okay. So, if 5 control signals, we are having 2 to the power 5, with 6 control signal we will be having 2 to the power 6. So, if it is 32, then next time it will be 64. If we add one more control signal, it will go for 2 to the power 7, 128. So, this is the number of states depends on the number of control signals, and it is exponential in nature. So, basically we are having a problem with this particular model checking algorithm, because the problem is known as your state explosion problem, because state space is exponential to the number of state variable. Now, though we have seen that we are having an automatic procedure, automatic algorithm to go for model checking for CTL formulas, but another problem that we are having with this model checking is your state explosion problem. So, now there some research works are going on how to contain or how to control this particular state space explosion problem. So, in our next class or next module, what we are going to see? We will see one particular approach to contain this particular state space explosion. Okay. I will stop here today.